Welcome to the Southern Technologies Corporation training presentation for the SmartScan NG system. Southern Technologies is located in Chattanooga, Tennessee. We have occupied this facility since 1990. STC has been serving the rail industry for more than 40 years. We service all Class I railroads and many short-line railroads, both in the United States and in 9 foreign countries. This training presentation provides a basic understanding of the SmartScan NG hotbox detector, installation, operation, and troubleshooting. This training presentation surveys the system in 2 main parts, the track hardware and the system electronics in the bungalow. The system electronics overview is followed by a closer look at the individual circuit boards that make up the NG system. Then we will examine system operation, and finally we'll conclude this presentation with descriptions of some of the reports the NG system provides. We begin with the track hardware. This slide illustrates the main purpose of the hotbox detector. The goal is to scan each bearing as it passes, comparing the reading to a preset alarm limit. Note the 2 angles depicted on the slide, each marked in red. The beam points at the inside of the bearing at a spot about 1 1/4 inches wide and 3 1/2 inches long. The bearing scanner beams out at a 45-degree angle at a bearing positioned between the gating transducers. Similar to the bearing scanner, the hot wheel scanner samples heat on each passing wheel and makes a comparison to a preset alarm limit. The scan line of the hot wheel scanner is about 3 1/2 inches above the crown of the rail. Here is a photograph of a typical site layout. There are 2 bearing scanners, 2 transducers, a paddle-type dragger, and track circuit connections. This photo provides a different view. Again, notice the position of the equipment. This slide shows a typical site layout. The layout shows 2 bearing scanners, 2 hot wheel scanners, 4 transducers, 2 gating and 2 advance, and a bungalow. Each bungalow should be properly grounded using recommended 8-foot ground rods at each corner of the bungalow with 6-gauge copper connected directly to the bungalow. Here is the bearing scanner module and mount. The scanner mount is made of ZA12 zinc, which is very rugged and does not rust. It is designed to operate in the harsh rail environment. The mount is electrically and mechanically isolated from the rail through the 4 shock mounts. One caution should be made at this point. There is a label on top of the scanner mount that says, "Do not exceed 50 foot-pounds of torque on 1-inch nut." Over-torquing the nuts could cause the cast clamp to break. 50 foot-pounds is more than enough torque to ensure the scanner mount stays tight on the rail. Next, here we see the hot wheel scanner and mount. Notice that the hot wheel scanner has a lot in common with the bearing scanner we just discussed. In essence, they are identical scanners with one exception. The hot wheel scanner requires the red filter frame inside the scanner housing. Note that the clamp parts of this mount are the same as those on the bearing scanner. Consequently, these parts are interchangeable. Clamps from the hot wheel scanner can be used to clamp a bearing scanner and vice versa. The direction of scan for the hot wheel scanner is toward the center of the track. As with the bearing scanner mount, there is also a cautionary label on top of the hot wheel mount that says, "Do not exceed 50 foot-pounds of torque on 1-inch nuts." The hot wheel mount provides for 2 grounding connections and has an opening for an airline attachment. This spacer kit is provided with each hot wheel mount. It should only be necessary to use this kit at locations running 115-pound rail. When beginning field installation of a new location, placement of the bearing scanners should be first. Start by selecting a crib that provides good tie spacing of at least 14 inches and that the ties are parallel with each other. Mount the first scanner to the rail. Use triangulation to place the second scanner opposite. The direction of scan is determined by the direction the large oval hole in the scanner is facing. When placing a scanner mount, it is important to choose the correct direction of scan. All scanners in the northern hemisphere should be placed scanning in a north or east direction. Compass direction is intended because there are occasions when a track is labeled something different. Direction is important because of the possibility of sunspots, which can interfere with the scan. Since the scanner points at a 45-degree angle, it is possible for it to face directly at the sun. This can occur during periods of the year when the sun lowers toward the horizon, primarily in the winter. This is why north and east directions for the scanner are required. It is important to install the debris port and vented debris port covers to prevent rodents from entering the scanner mount. These two pictures show correct and incorrect mounting. The left picture shows good tie spacing and the ballast has been removed around the scanner base. The right picture shows the crib spacing is too narrow, with the scanner possibly touching the tie. If a scanner is making contact with anything, a tie, a rail clip, or ballast, spiking noise can be introduced into the system and cause false alarms. The scanner mounts should be freely hanging on the bottom of the rail. This is the 2500-512 AC scanner. This scanner is made up of 3 systems: heaters, shutter solenoid, and Pyro block. This picture shows the scanner cover. Before plugging a scanner into a system, it would be a good idea to check the identification plate to make sure you are installing the correct type scanner. This is the main body of the scanner. The heaters are controlled by the processor in the NG system. Its primary purpose is to keep the inside of the scanner dry and help melt snow in the winter. The heaters are set up on a cycle time. This table shows the length of time the heaters will be on with reference to ambient temperature readings. This is the Pyro shutter insert on the Type III scanner. Notice the shutter solenoid and location of the Pyro lens. This is the Type III Pyro housing assembly. It is mounted in the bottom of the scanner and is the primary infrared input device for the system. The Pyro assembly consists of 2 small circuit boards potted into an aluminum cylinder. The Pyro board contains the pyroelectric device, amplifier, and a sky shot circuit. The device is AC coupled and responds to rapid changes in temperature from a baseline. The baseline is established from the temperature the device reads on the bottom of passing cars. The sky shot circuit protects the baseline from rapid changes caused when a car that does not have a complete body passes over the device. Without the sky shot circuit, a car passing with an open body would cause the baseline to drop dramatically. Consequently, the very next bearing would appear to be extremely hot, resulting in a hot box alarm. Notice that, like the rail mount, the Pyro assembly has shock mounts attached to it. This allows shock absorption from many different planes and keeps the Pyro assembly very quiet, even in a high vibration environment. There are 2 screws in the sides of the Pyro assembly. These screws are set at the factory and should not be adjusted in the field. A periodic cleaning of the lens is the only maintenance required on the Pyro block. Cleaning is recommended about every 30 days. When cleaning, it is important not to overly scrub or use products that contain alcohol or ammonia. This can cause the coatings on the lens to be compromised. The Pyro assembly has a removable lens cap. If the lens should become extremely scratched or deteriorated, a new lens can be installed. If you install a new lens, it will be necessary to recalibrate the scanner. The shutter solenoid mechanism performs two functions, keeping debris out of the scanner and post-train integrity testing. As a train enters a location, the shutter door opens. The resistive heaters will begin to heat when the shutter is activated. The door stays open through the entire train. After the train has passed, the shutter door closes and the system samples the heat from the shutter resistor. This sample is compared to a preset limit. If the resistor sample exceeds the limit, the integrity test is passed. If it is below the limit, the system will call it a cold resistor. Each Type III scanner will be shipped with a black filter frame in place. If the scanner is going to be used as a hot wheel, we will supply a red filter frame in a separate bag. Whether you use the black or red frames, it is important to note that in order to calibrate a scanner, the black frame must be in place. A periodic cleaning of the filter lens is necessary. STC has supplied a lens cleaning kit that contains soft patches and lens cleaning fluid. Cleaning is recommended about every 30 days. Cleaning fluids that contain ammonia and high percentages of alcohol should be avoided. These are the NG scanner cables. The cables can be purchased in any length. Our standard cables come in 65 feet, 100 feet, and 130 feet. Each cable comes complete with connectors on both ends that have been potted in a polyurethane compound. The scanner mounts are designed to be interchangeable from side to side. When mounting the cable, leave 6 inches of scanner cable from the mounting plate. Now let's move on to the STC transducer. Each system is equipped with 2 gating transducers. The transducer is made from a horseshoe magnet with about 3,200 winds of nylon wire. The wound magnet is then placed in a molded resin shell and potted with a polyplastic compound. This makes the unit weather-tight and keeps the magnet stable in a high vibration environment. The transducer functions by creating a magnetic field around the crown of the rail. When a metal wheel passes through the field, it changes the field, creating a pulse from the transducer. One of the most frequent complaints regarding transducers is that they do not stay tight on the rail. STC has put together a group of locking hardware that has proven to be very effective in this regard. Each transducer comes with bolts, Nord-lock washers, and nuts. It is important to use all of this hardware correctly. The Nord-lock washers are a 2-piece washer system. If half the washer is lost, the Nord-lock will not work. Over-tightening the bolts can lead to problems as well. The plate bolts through the rail should be torqued 10 to 12 foot-pounds, and the bolts holding the transducer 8 to 10 foot-pounds. After the scanners have been positioned on the rail, the next step is to install the transducers. Each transducer comes with a mounting plate. STC produces 2 mounting plates, a plate stamped 112 to 131 pounds, and a large plate stamped 131 to 141 pounds. If your rail size does not match these plates, contact STC and we will inform you how to proceed. Use the tables in the manual to determine the correct measurement for the rail size you are working on. This table shows information for transducer 1. Measure from the back side of the clamp to the notch on the mounting plate. Use the plate as a template to mark accurate hole placement. It is important to have the plate tight against the top of the web. This table indicates the information for transducer 2. This slide illustrates the typical site layout for an AEI system. Some locations may have an AEI system integrated with the NG system. Adding AEI to a location involves installing the towers and antennas, running the RF cables to the bungalow, and installing the AEI interface in the bungalow. We will discuss more about AEI later in this presentation. The purpose of an AEI system is to read the tags on a car and pass this information onto the NG system. The NG will match the tag data with the train data for a complete report. The 2300-775 AEI interface connects to the NG through the DB9 plug and a null modem cable. This package contains the transcore board set, AI1200 reader, and AI2200 RF module. Supply voltage for each unit is 12 volts DC. The indicator lights will show power, antenna 1, antenna 2, and RF lock. The RF lock light indicates that the antenna is locked onto a tag. RF 0 and RF 1 indicate power to the antenna, and PWR is line power, that's 12 volts plus DC. All of the setup parameters have been taken care of by STC. The null modem cable will be plugged into one of the COM ports on the NG system, and the AEI must be turned on in the equipment menu of the NG system. This photograph shows the temperature probe components. There are three basic parts: the radiation shield, the EMI suppressor assembly, and the temperature probe circuit board. Over the years, there have been a number of changes to the temperature probe. The EMI suppressor assembly, along with the metal ring on the bottom of the shield, reduce the possibility of RF interference getting into the system. The circuit boards are also now potted in a polyurethane compound to make them better weather resistant. The probe provides temperature for three functions of the system. It provides the temperature for the heater cycle in the scanner, shows the temperature on reports, and provides the temperature for voice transmissions. It is not, however, the reference for the scanners. Clearly, there are a number of potentiometers on the temperature probe board. These pots are used for calibration at the factory. There is nothing field serviceable on the temp probe board. If the temp probe board fails, it usually goes to one of its max temperatures, minus 40 degrees or positive 149 degrees Fahrenheit. If this occurs, the only option is to change the temperature probe. This slide shows the connections to a battery charger powered by line AC. The charger should be set at 14 volts DC when using the supplied Delco S2000 battery. To ensure proper charging, make sure the temp probe from the charger is connected to the battery minus. Now we turn to the bungalow and consider the system electronics. This is the SmartScan 2300-500 NG system. It is comprised of two main modules, the 2300-501 chassis and the 2300-502 System Interface Control Module. It has expanded capabilities above all previous hotbox detectors. More COM ports have been added to allow easier external equipment integration. Additional surge protection has been added on each incoming line, and a smaller physical package to fit into any bungalow or signal case, just to name a few. When the system interface module is removed, the component in the upper chassis will be exposed. This circuit board is the Interconnect board. It is the primary connection point between the track-mounted equipment and the system in the bungalow. This is the voice speaker mounted on top of the NG chassis. It will announce all of the voice messages in the bungalow that will be heard on the radio. There is a volume switch located on the right side. Whether the system you are working with has 2 or 4 scanners, bearing and hot wheel, All of the shutters and heaters are controlled by two heavy-duty solid-state relays. The top relay is DC and controls the shutters. The bottom relay is AC and controls the heaters. The heaters are set up on a timed cycle from the processor that we discussed earlier. The cycle will vary by the reading received from the temperature probe. The scanner connectors are mounted to the bottom of the chassis. The four scanner connections are identical, so it's important to make sure that you plug your scanners into the correct connector. The easiest way to tell if they are not in the correct position is during AutoCal. When the laptop says it found heat on a scanner, make sure the label in AutoCal matches the scanner on the track with the heat source on it. To improve the surge protection of the system, the NG system has a built-in Faraday cage. Each line coming in from the track goes through a universal transient barrier, or UTB. This includes the transducers, track circuit wires, auxiliary alarms, telephone line, and temperature probe. The UTBs are closed-circuit devices. If you measure the resistance across one, input to output, and it is open, then it is bad or has been blown. Since we provide inputs for multiple auxiliary alarms, there will normally be a couple of UTBs that are not utilized and can be used as spares. Now, let's take a closer look at the System Interface Module. The 2300-502 System Interface Module is comprised of three circuit boards: the 2300-105 Interface Board, the 2300-100 EPCC Board, and the Velocity Modem Board. This picture shows the module with a Velocity modem installed. The COM3 DB9 cable has been replaced with an RJ45 plug. COM6 has a null modem adapter added to make it possible to connect to the Velocity modem with a laptop. This interface board contains the COM port circuits, the speech data chips, input filtering for all the input equipment, and potentiometers to adjust the audio level to the radio and the DTMF level. On the bottom right-hand corner of the board is a crowbar circuit. The crowbar circuit is there to protect the module from overvoltage levels. The crowbar circuit is set to open at 18 volts DC, and a red LED will illuminate. The loading jumpers for the transducers are located on this board, J201 and J202. The loading resistors offer three levels: 100 ohms, 220 ohms, and 470 ohms. All units are shipped with the jumper in the 100 ohm position. Using the loading jumpers will be covered later in this presentation. The NG systems offer 6 COM ports. COM1 will be the most common for laptop use. The configuration of the remaining ports will depend on firmware. On the side of the NG interface module is a bank of indicator lights. The label on the metal cover should show the identity of the lights. A full description of the lights can be found in the user's guide. The two lights on the top row are for the dual processors. The COM processor and reader processor light should be revolving on and off in a slow, steady pattern. These lights indicate that both processors are running correctly. If they're on solid or flashing rapidly, the system has encountered a problem. This may require flashing the program into one or both of the program chips. This is the 2300-100 EPCC board. This is the main processing board of the system. Each processor controls different functions of the system. The reader processor monitors train activity, alarms, talker messaging, and system integrity. The COM processor controls the serial ports and communication to modems and polling systems. There is a reference voltage potentiometer on this board. It will be set by STC at 5.0 volts DC. Now, let us look at operation of the system as we look at system setup, alignment, and calibration. Ensuring that the scanners are in the correct position is very important to the system. Alignment could affect the levels of temperatures that the system reads. First, mount the alignment fixture on the track, on the center of the transducers. When placing the alignment fixture on the rail, use the open side of the fiberglass channel as the mark. Then, using the same triangulation method used to place the scanners, make sure that the alignment fixture is square on the track. Insert the target sight into the alignment fixture and place the mirror block on top of the scanner. It is not necessary to determine magnetic center on the transducers. Physical centering is acceptable. To see where the scanner is looking, look through the hole on the target sight and see if the X is in the circle. There are two adjustments to scanner alignment, a vertical adjustment and a horizontal adjustment. If a vertical adjustment has to be made, loosen the 1-inch nuts and slide the scanner forward or backward on the rail. If a horizontal adjustment is necessary, move the 2 nuts on the clamp bolts up or down the threads to rock the base plate under the rail. This changes the cant angle, or the angle that determines where the scanner looks at the bearing. The alignment fixture has ruler scales on both the vertical and horizontal bars. The correct placement of the scanner is vertical, 18 inches plus or minus 1 inch, horizontal, 7 1/4 inches plus or minus 1/4 inch. When making a horizontal adjustment, be sure that the nuts are moving equally on each bolt to keep the scanner mount parallel to the rail. Wheel scanner alignment is very simple. Extend the bar of the alignment fixture all the way out. Measure down from the front and back of the mount. These measurements should be equal. Use the same 2 bolts that the bearing scanner uses for horizontal adjustment. Vertical alignment is not necessary, as long as both hot wheel mounts are sitting between the gating transducers. Each alignment fixture comes with a transducer height bracket attached. This bracket is long enough to make sure the transducer is not tilted on the rail. To adjust, loosen the transducer nuts and pull the transducer up in contact with the bracket. Tighten the nuts. This should put the transducer at approximately 1 5/8 of an inch below the crown of the rail. Do the same to all of the transducers at this site. Be careful not to over-tighten the transducers. If your alignment fixture does not have the height bracket, measure down from the crown of the rail and set the transducer to 1 5/8 of an inch below the crown of the rail. The 2100 810 NG heat source is designed to calibrate hot box detectors in all types of weather conditions. It can operate from well below 0 to well over 110 degrees Fahrenheit. It is important to make certain the filter frames in the scanners have been cleaned before calibrating. Select the desired temperature. Plug it in and wait for about 10 minutes for it to come to temperature. The temperature has been reached when the needle in the window stabilizes in the center. Place the heat source on the scanner and you're ready to calibrate. The power cord from the heat source should be toward the front of the scanner to indicate the heat source is mounted correctly. The NG heat source has a bracket mounted to the bottom of the unit that will allow the heat source to set directly on top of the scanner. To place on the scanner, slide the heat source from the back of the scanner forward until it stops. This will provide correct placement of the heat source. The scanner is now ready for calibration. In extreme temperatures, whether hot or cold, always make sure the heat source is at the proper temperature level before starting AutoCal. The 2300-970 scanner breakout box is designed to be connected between the scanner and the detector to facilitate measurement of scanner signals. With the supplied adapter cable, the breakout box can be connected at the detector end or the scanner end of the scanner cable. To communicate with the system, a laptop running a terminal program set at the correct baud rate is necessary. The baud rate from the factory is 19,208 in 1, with no flow control. If you're using a laptop with Windows 7, the terminal program TerraTerm version 4.69 will work with either the 32-bit or 64-bit Windows. Press Escape and the main menu appears on the screen. All information and functions begin with this main menu. To access the reports, select the corresponding letter with the desired report. We will look at some of the reports in more detail in a moment. This is the Setup menu. The Setup places the system in the right parameters for train scanning and alarm monitoring. One of the functions of the Setup menu is Load Default Setup Parameters. When they are made available to STC, our software programmers will insert the correct data in the right location. The only thing remaining for the service personnel to add is the date, time, and milepost. This is the System Function menu. This is the menu where you will find many of the test functions on the system. In order to run a calibration, the heat source should be up to temperature and placed on a scanner. Then select the System Function menu and AutoCal. This system will complete the AutoCal unattended. It is a good idea to watch the AutoCal a few times to see what takes place and what temperature it starts out at and the pot settings. This will help with troubleshooting scanners in the future. In this final section, we turn to several of the many different reports the SmartScan NG system can provide and demonstrate how to analyze some of the data to assist with troubleshooting. This first slide is a train summary report. The top of the report is referred to as the header. It contains summary information about the location, software versions, and alarm limits. The first three columns provide a sequential index number, the date, and the time each train passed through the location. The next two columns of interest to us are the TO1 and TO2 columns. These numbers reflect wheels passing over each of the gating transducers. Since all of the wheels pass over each transducer, these numbers should be equal. If they are off by more than 10, an integrity failure will be announced. Before changing anything in the setup or software, it is important to always check the physical condition of the hardware on the track. This goes for scanners, gating transducers, and advanced transducers. The transducer hardware should be tight and the height set to 1 5/8 inches below the crown of the rail, or use the transducer gauge on the alignment fixture to set the height. After checking the physical condition of the gating transducers, it may be necessary to adjust the loading. The loading increases or decreases the sensitivity of the transducers. When reading the information from the train summary report, the transducer that has lower count is usually the one that needs adjusting. The loading is controlled by jumpers and resistors that are in parallel to the transducer. The jumpers J201 and J202 are located on the System Interface Control Module. Each jumper has three possible settings: 100 ohms, 220 ohms, and 470 ohms. Increasing the resistance increases the sensitivity of the transducer. If a miscount is still occurring, an additional adjustment can be made. Each of the scanners in a system are calibrated with the same heat source. Because of this, the average temperatures from the scanner should run very close to each other. In the columns labeled Average Rail East, West, these temperatures should be within 5 degrees of each other. If they're off, another recalibration and checking of the alignment is in order. The same heat average is true for the hot wheel scanners. These temperatures should be within 10 degrees of each other. If they are not, alignment and calibration should be checked. Make sure to switch the red filter for the black filter in the hot wheel scanner before calibration. Always replace the red filter in the hot wheel scanner before leaving the location. The AMB temp column is read off the temperature probe for a given train. If this temperature reads minus 49 degrees Fahrenheit or plus 150 degrees Fahrenheit, this indicates the temperature probe is faulty. The battery voltage is given for each passing train. The battery voltage should remain consistent among the trains in the summary. If the battery voltage is fluctuating, it could indicate charging problems or a battery going bad. You should see no more than a 1-volt difference from train to train, whether the system is operated on AC power or solar. At a solar location, the battery voltage will decrease from train to train during periods of darkness. This is normal. The concern should be if the voltage changes dramatically between sequential trains. The train detail report expands on the information from the train summary report. The header information is similar to the train summary report, providing date, time, speed, number of axles, direction, milepost, temperature, and battery level. Just below the header is a section labeled Rail. This rail section can provide critical troubleshooting information. This gives the maximum temperature each scanner saw for this train, the average of each scanner for the entire train, and the integrity resistor values for each scanner. To determine if the train passed the post-train integrity test, look at the columns labeled Resistor Red and Resistor Required. If the red number exceeds the required number, the test is passed. The next column, labeled CF, stands for correction factors. If the correction factors are above 25, it would be a good idea to look a little closer at that rail, as this may indicate that the shutter is not working properly. If hot wheel scanners are present, a section will appear just below the rail section with the hot wheel information. This section of the reports shows the TO1 and TO2 transducer counts. This information is the same as the summary report. The filter columns refer to performance issues of the transducers. Filter A refers to the pulse width filter, which is set at 3 milliseconds. Any pulses on the transducer less than 3 milliseconds will be filtered out, and the counter will be incremented. Filter B refers to the timing between transducer pulses and is set for 300 milliseconds. This means if a pulse is received and then a second pulse is received in less than 300 milliseconds, the second pulse will be filtered and the counter incremented. This section shows the current firmware versions in the system. This section of the train detail report is the system alarm or integrity failure messages. This is essential to troubleshooting, as this area will provide written messages about system performance and will direct the technician to the specific part of the system that requires attention. The messages can include some of these: cold north rail, cold south resistor, and high-range transducer miscount. By using these messages, a technician can find a connection to a specific module in the system and make the repair or replacement. A complete list of these messages can be found in the STC User's Guide. After all of the header information, this report displays axle-by-axle data. It shows the maximum temperature read by the scanner for each bearing, how long the wheel was in the transducer gate, and the timing between axles. The on and off times can be used to help troubleshoot transducer problems. The east rail and west rail columns show the actual temperature read for a given axle on the train. Each bearing on the train is sampled multiple times, and the maximum value is shown. If wheel scanners are present, the east wheel and west wheel columns will show the actual temperatures read from each passing wheel. Each wheel is sampled 48 times, and the maximum value is shown. The on time indicates how long the axle was in the gate in milliseconds. The gate is determined by the distance between the two gating transducers. By using the on time and the direction of the train, a transducer missing pulses can be identified. The on times should remain consistent throughout the entire train. The only variance is if the train is speeding up or slowing down. Whatever the change, it will change slowly. If there is a long on time, then one transducer pulsed and the second transducer missed. If the train direction is northbound, it should cross transducer TO1 first. A long on time indicates that a pulse was missed on TO2. If the report shows a number of trains with this miscount, then adjusting the loading on TO2 would be in order. The same would be true on a southbound train. It would cross TO2 first and may indicate an adjustment on TO1 is necessary. If an adjustment is necessary, jumpers J201 and J202 on the interface are the locations of the transducer's loading circuits. Increasing the jumper setting will increase the sensitivity of the transducer, and decreasing will reduce the transducer sensitivity. The PW1 and PW2 columns refer to pulse width in milliseconds. As a wheel is passing over a transducer, this is the time the wheel was over the magnet. These numbers should remain close to each other because of the speed of the train. This is the System Status Report. The System Status Report gives a complete picture of how the system is set up. It shows all the alarm settings, the equipment setup, the status of the messages, and the software versions installed. After all the setup is complete, a hard copy of this report at each location can be useful if something gets changed accidentally. The first part is the header. This information is similar to the train summary report. The alarm limit section shows all of the alarm limits. The alarm limits are normally determined by the railroad. A complete explanation of all the alarms is available in the user's guide. The equipment section of the report allows the user to customize the hardware profile for each location. Some locations may have different hardware, such as Hot Wheels or high-wide detectors. There are 3 components in this section that call for some additional explanation. First, the winter cycle. The winter cycle was put in place to assist areas of the country that have a large accumulation of snow. This option will increase the time the heaters are on. In the coldest temperatures, it will double the heater cycle time. Second, the gate distance is the distance from center to center of the gating transducers. The gating transducers are used by the system to calculate length of train and speed. If the correct physical distance in inches is not in the setup, some of the detector information will not be correct. The distance can be entered in tenths of an inch. Third, the selected modem. Currently, all of the new NG systems being delivered have a velocity modem installed. Software is still being developed for this application. The message menu provides access to customize the speech heard from each detector site. Each system will monitor the time from its last calibration. Those dates and times are available in this section. The COM port information is available in the Port Settings section. It is important to make sure that the COM port baud rates match any system being connected, a laptop or a polling system. The DCS parameters refer to a polling system. This section will vary depending on type of polling used. The next area shows the current software versions in the NG system and the date tested and serial number of the EPCC board. The last section of the system status report is the integrity resistor tables. After calibration has been complete, the system will say resistor test beginning in 20 minutes. After the 20 minutes has elapsed, the shutter test will begin. The shutter will open and close for 480 seconds. After all the samples are gathered, they are populated in the resistor table. There are 3 possible outcomes for the resistor table test: valid, invalid, or pending. Valid means the test was successful and the system is ready to go. Invalid means the temperatures the test expected to see are not on the table. It will try to run the test a second time. If it still fails, the label will remain invalid, and the interim test in the software will be used for post-train integrity testing. The interim test is 4 distinct time periods with fixed resistor values. It does not contain as many samples as the table. Checking scanner information, average heats, and resistors read on the train detail report can help determine if the scanner needs to be replaced. Pending means that the test is yet to be run. If the system has a train passing through the location before the resistor table has been run, the detector will use the interim test on that train and will restart the 20-minute counter. After 20 minutes, it will run the resistor table. The final report is the event log. When looking at an event log, we are looking for processor resets or train data not being transferred to the polling system. This report will also provide information on train arrivals and any time the system is accessed. Thank you for viewing the Southern Technologies Corporation training presentation for the SmartScan NG system. We trust you have found this presentation to be useful.